Okay, so in this section, we will explore a real-world case study on that demonstrates the edge-powered industrial control, and it will highlight how the edge devices and the computing and the cloud computing and IIoT components can modernize, can help to modernize automation system. Okay, systems. So in the past, um, control field devices basically were isolated in a dedicated control network, and where the field level devices would exchange information directly with the control hardware like DCS or PLCs. And everything is stayed local. Okay, so everything is stayed local, which was simple, and the benefit was it was simple as well as it was secure, but uh, but it is limited in its flexibility and scalability. Now things have been changing. Things are changed now with the massive storage capacity and centralized computing power available through the cloud. Industries are now moving many of their control and analytics functions to the cloud platform because the intelligence will be utilized there. So, however, not all the computations are suitable for the cloud execution, especially those requiring fast deterministic control near the plant floor. So, what is the solution? So this is an example, and it is taken from an IEEE paper, uh, and it presents a platform concept. It is giving us a platform concept about that blends the cloud computing with the industrial control through the edge devices. This was actually implemented on an automation cell, making it a real industrial scale demonstrator, not just a simulation. Okay, so and the technology that is used is the AWS green grass, which is Amazon's edge computing framework, and that enables the local processing, messaging, machine learning interfaces directly on the edge device. This is a great example for bridging the gap between the traditional control systems and modern cloud-based infrastructures for using the edge computing. So now let's look at the actual setup of the automation cell used in this industrial demonstrator. In this setup is sensor guided and designed for pick and place. So this is sensor guided and designed for pick and place operation. And you can see here that the KUKA robots, robotic arms are placed on either side of the white conveyor. This is the white conveyor. You can see the white conveyor belt here. These robots are responsible for moving a cylinder back and forth across the conveyor. Okay, and a typical repetitive task in manufacturing settings. So to enable the precise control, the two laser distance sensors are also used, installed on the both sides of the conveyor belt, and uh, these sensors are measure the relative position of the cylinder in the real time as it moves along the belt, and the entire setup is controlled through an edge computing system leveraging the AWS Greengrass. It demonstrates how the traditional industrial control can be enhanced using the smart edge devices integrating with the cloud platform. So this gives us an hands-on view of how the edge-powered automation may work in the practice. combining the sensors, robotics, and the real-time decision making. Okay, now in this slide, we are looking at the full architecture that enables the edge-powered industrial control from field level all up to the cloud uh, level. At the bottom, we see that this at this field level, we see the robotic arm here, and we see the motors, and and other physical devices and sensors. So these are the real world components generating the data, executing the physical action. Okay, so the data is generated here, the physical action is here, all of it. Now this data moves up to the edge layer. The data is moved to the edge layer where specialized edge devices are deployed, and these edge devices like this one and this one. So these edge devices are what specialized edge devices, and these devices carry out the various tasks, variety of tasks. Some are doing like data processing, like filtering, cleaning, and compression. Cloud assistant control, where some analytics or control logic can be interacted with the cloud system. Data forwarding, to push the relevant data to the upper layer only when it is needed, and and in fact, a gateway module inside the cloud, inside the edge, handles all the processing and routing tasks. So this architecture supports the real-time sort of control loop. Okay, so a sort of a real-time control loop directly at the edge. So it has a real-time sort of control loop. So this architecture supports the real-time and helping to reduce the latency and avoid bottlenecks in the cloud transmission. As we move further up into the cloud layer, we enter a more centralized. Here you see this. It is more centralized. Environment, and where the data repositories are maintained. Here the data repositories are maintained, and here the data is stored for long term and may be used for model training, batch analytics, or even for the historical analysis. Okay, so here we can do let's say the model training and batch analytics, and also the historical analysis. Okay, so we we also see a connection to the environmental layer, which may include the third party data sources, such as like pricing, weather forecast. Okay, so it shows the pricing, it shows the weather, and so these can enrich the decision making process, because this data, when incorporated, it will improve the decision making. This environmental interaction, which will improve, this will further will improve decision making process. Okay, so overall this figure shows clearly that the security mechanism like data encryption and firewall protections are enforced at every layer. We see that it is being taken care well, and this ensures that the data flows are not only efficient but also the secure, but also secure. So overall, this architecture provides it provides like a hybrid, intelligent model. Okay, and it leverages the real-time responsive of the edge and the deep processing power of the cloud. So all is integrated in a secure way. Let's go more deeply. So at the very bottom of the automation pyramid, we see that we have the what we call the field level. And this level includes all the physical automation components that interacts directly with the process. These are devices like robots, grippers, frequency converters, sensors, motors, and all of these are collectively referred to as the field devices. So all the field devices are there. Now, what makes the field device so critical is that it directly is responsible for it is directly responsible for for making or executing the actions. Okay, so it is making the actions, and also it is capturing the real-time process data. So that means any delay or failure can be here can have the impact on the performance and safety of the entire system. So field devices are tightly linked with the actual physical process, and as a result, they need to operate on very tight time constraints. Very tight time constraints. They often need to react faster than typically process cycle times, which can range from just a few microseconds to like milliseconds. So they have to be very quick. So in these environments, two things become extremely important. So the first thing is latency, and the second thing is reliability for practical purposes. So latency means which refers to the how fast a device can respond or communicate. So latency is how fast a device can respond or communicate. And the reliability is about the meaning that the system must perform without failure, without failure under all conditions. Okay. So together, these two define how well the field level communication infrastructure can support the demands for the modern industrial automation. Okay, so the second thing is now when we move up to the layer to the IIoT devices, these devices are special in sense that they perform two parallel operations. They perform two parallel operations. The first one is that they act as a field device drivers. That means they establish and maintain connections with the physical world devices such as sensors and actuators, and they have to meet hard real-time requirements. So this is important because these devices are responsible for tightly controlling or acquiring the data from the field instruments. And since industrial environments use a variety of field devices and communication protocols, the IIoT device must support sort of multiple drivers all deployed on the premises on a premise for the exact purpose. The second function is for IoT is mainly the communications, which appears to be the first one, but it is the second thing after getting the data. First one is the connecting with the devices to collect the data. So in the second function of the IoT devices, which is communication, it communicates with the edge gateway using these standard protocols like TCP or UDP, IP. Now, this communication is not time critical. The first one with the devices was critical, but not this. This is not um, as much as it is not is very time critical. This is not very time critical. So it is either non-time critical, non-real time, or almost soft real time. It's better to call it soft a real time. Okay, so this is critical, real time, critical real time. Okay, so why the second communication? Why is this second communication channel like very important? Because it is the path through which the IoT device sends the data upstream. This is one of the important aspects of IoT. It receives the software updates, exchanges the data instructions through the high level applications. So essentially, IoT devices are the intelligent agents at the edge, bringing the real-time physical world with the flexible data driven one. So on one side we have flexible data driven information world, digital world, and on the other side we have the real-time physical world. And here um, IIoT devices uh, are at the edge, which make the connection, which actually enable this interconnection or bridge. Okay. Okay, let's move to the next slide. Okay, now let's talk about the edge level. So this is the intermediate layer, and it sits upon between the cloud and the services at the top, and the physical field devices at the bottom. At this level, we distinguish two important entities we discussed before. One is the edge gateway, and other is the uh, your edge devices. Both of these work together to handle data forwarding and shaping, data shaping between the layers. So let's talk about the edge gateway. Edge gateway is basically the hardware component, and it acts like a central node or central hub for the communication between the cloud and the IoT devices. It allows the IoT devices to push the data acquired from the cloud when needed, and it also used to pull. It is good to push the. It is basically to push the acquired data up to the cloud, and also to pull. So it can push and it can pull data to and from the cloud. Okay. So now coming to the edge device, this one. Now coming to the edge device, this is more like a software container, this edge device, and it lives inside or alongside the edge gateway, and its job is to perform the data shaping. It has the data shaping functionality on the edge. So even if there is a disconnect from the cloud, the process itself will continue to run without any interruption. So it is self-contained data shaping mechanism. So in short, the edge level makes the system overall, the system resilient, responsive, and also the cloud independent when needed. Okay, when needed. All right. Okay, let's move to this next slide. Okay, now it's so let's now look at the top level of the architecture with the cloud. So the cloud level consists of standard cloud components, and such as the APIs or storage services or some kind of like analytical engines, and even various cloud-based services and applications. All of these work together to support the industrial systems by providing compute power. Basically, what they are providing us the compute power, very strong, and then they are also providing us some kind of like a data storage, okay, and also additional services. And these services can be, for example, we want to monitor, we want to control, take action and control something. And even the most important one is the optimization. This is the most of the time we are doing this thing, optimization. So above that, we have the after that we have the environmental layer, and this layer is mostly used for visualization and consumer uh, for the consumer side applications. For example, the dashboards. Okay, so dashboards, for example, or connectivity with the some kind of like dashboards that displays the real time or KPIs. Okay, and or the process metrics for, and these dashboards are basically used by so many the decision makers based on to see used. It is most of the time it is used by decision makers, and what they do is they actually watch some kind of matrix matrix process, but we call it performance or process matrix. Okay, processed or performance matrices. So it is very critical that everything should reflect its proper meaning. Any trouble will not help the decision makers, and they may come up with the wrong decisions, and then the whole system may be disturbed. Okay, now comes the interesting part: cloud assisted control. Cloud assisted control, this is where the IoT devices offer offload the heavy processing task to the cloud, and instead of doing complex analytics or monitoring locally, what they do is they send data to the cloud and let the cloud do the work, and then they take the decisions based on those results. So for instance, after cloud based analytics, a device might adjust maybe a process parameter such as temperature or speed or cycle time to improve the performance. Okay, so this gives us a hybrid control model where some logic remains local and some is powered by the cloud. So the overall, this provide us the hybrid control model. Why we are calling this hybrid? Because in some logic remains, some logic or AI remains local, and some logic or AI is powered by what you call cloud. Okay, so it brings the overall, combining these two things, um, it brings both efficiency as well as it brings the flexibility to the overall IIoT system. Okay, right. Okay, so what we have in this slide is, in this slide we examine the hardware configuration of the robotic automation system powered by the Raspberry Pi devices. And each robot is equipped with a servo electric gripper, and enabling it to perform like force guided gripping action with precision. So these robot gripper pairs are connected with the Raspberry Pi units, and which actually which is a function of the industrial internet of thing device. So we refer to these IoT devices as IIoT device 1 and IoT device 2. So their main task is to relay control commands and receive the sensor feedback. So these are the two Raspberry Pi devices, and these devices communicate using the MQTT for non-real time, and UDP for real time. Okay, so for MQTT, you can say that for non real time data, and they use UDP for real time control loops because they are lighter. So additionally, this one Raspberry Pi is configured to manage to manage the frequency converter, and this frequency converter that controls the conveyor belt. So you see, this is controlling this conveyor belt to manage the frequency, as well as the two laser sensors which are here. Uh, all of these components are connected using some kind of like serial communication device. On the right side uh, of this is the architecture is basically visually representing what's happening here. So what we can see, how both IoT devices are interacting with the edge devices through the serial communication network, and the edge devices then communicate the material to the cloud through the two protocols. Okay, so the overall this architecture is supporting secure as well as the scalable industrial control. Okay, so some few comments here also about the same. In the slide is showing the role of the Raspberry Pi in this industrial setup. So from hardware perspective, the Raspberry Pi acts as an edge gateway, and it provides the connectivity to the cloud. But from a software perspective, it performs a dual role function, like it is functioning as a IIoT device as well as the edge device. Okay, so it is combining both roles because its primary task is cloud connectivity, and we refer to this Raspberry Pi as edge gateway. Now, in the real time performance, the real time performance is critical, especially for when we are communicating with this the KUKA robot. So each control packet sent by the robot must be acknowledged within the what you call a specific time. Okay, so each control packet that we send by the robot must be acknowledged within a strictly time window, um, so that we have the reliable operation. So in this configuration, IIoT devices, these 1 and 2, um, along with the gateway, communicate over the two channel. One is the real time and the other one is the non-real time channels. So the real time channel uses the UDP. Um, while and why we are using UDP? Because it minimizes the delay, and it ensures the responsiveness. On the other hand, the non real-time channel uses the MQTT data, which is a lightweight publication. It is a lightweight. It's a lightweight but publish subscriber. Publish subscribe protocol for sending and receiving for sending the devices between data between the devices, IoT devices, and the edge and the cloud. So this separation of channels. So what happens here? We have the separation. This separation of channels enables number one, reliable control, and also scalable scalable data exchange, and it is happening simultaneously. Okay, moving to the next slide here. What we have in this part is we we actually discuss how the edge devices and the cloud systems work together. Okay, in a modern in a modern industrial setup. Okay, all right. So the edge device software running on the edge gateway plays a crucial role, and it performs the it performs the first aggregation of the data received from multiple IoT devices, and these messages are combined into one MQTT packet and then sent to the cloud uh, using the AWS IoT services. At the same time, the edge device is also capable of processing the data coming from the cloud, and this allows for pre-filtered and supervised execution of the controlled actions and real-time adjustment of any of the process parameters. So now, now considering a scenario where the IoT device needs to update or upgrade industrial software or control logic, the cloud enables this seamlessly, making it possible, for example, changing the speed of a conveyor belt remotely and in real time using the cloud assisted control. So and moreover, the edge device includes this important buffering system. This system caches the process data, in the event the cloud is disconnected. And once connectivity is restored, the buffer data is securely forwarded to the cloud, encrypted by the security protocol. So finally, all the data gathered is processed by the specialized analytics applications running in the cloud, and it it further provides the insights and control intelligence to the overall system. Okay. So we will discuss the analytics in the next topics uh, further. So let's move to the next slide. Okay, so this is the last slide in our this topic 3. So it continues to talk about in this implementation, the system actually extracts two key types of information from the process data. One is the operating data and the other one is the power consumption. And this includes the metrics like the total operating time and the activity statistics of the activity of the both robotics grippers and the distance traveled by the conveyor belt and the robots. So these metrics are valuable for predictive maintenance applications, such as like estimating the mean time between the failure. This is the most crucial thing in the factories or machines which are working in. We are very careful about calculating this thing accurately and exactly. And then the second feature is the cloud system uses the parameters like the supply voltage, the current information, and the operating times, and it helps to estimate the total power consumption in kilowatt hours for the industries. So what's notable is that this estimated consumption is dynamically correlated with the real-time electricity price rates from the variable from the available energy suppliers. So using this information, the system can compute the appropriate conveyor speed based on a cost limit set by the user. And this ensures that the operation stays within the desired energy budget, because it's not here in Saudi, but in the world, the price rates for the electricity varies with the hours, and even the day and times. Overall, in 24 hours it varies. So finally, all of this data, both the power consumption and the operational matrices, this is exposed to the user through a mobile application, maybe by as through by a third party solution. So this enables the real time monitoring. So the main thing that we achieve is what? Real time monitoring. And also the other important thing is informed decision making. Okay. And you are doing it virtually from anywhere. Virtually from anywhere. Okay. Thank you very much. This ends our topic number 3. Assalamu alaikum warahmatullahi.